This explanatory film is about our electrical machinery course, and I plan to present the solution of the example on slide number 180 of the lecture notes. That slide says that it's one of the examples in the lecture notes. A 240 kilowatts, 240 volts, 600 RPM separately excited DC generator has an armature resistance R sub A equals to 0.01 ohms and a field resistance of 30 ohms. The field winding is supplied from a DC source of V sub F 100 volts. A variable resistance R is connected in series with the field winding to adjust field current IF. The magnetization curve of the generator at 600 RPM is given below. These are the corresponding pairs of field current with respect to induced armature voltage. And if the DC generator is delivering rated voltage and is driven at 600 RPM, the question requests to determine A. Induced armature EMF, B. The internal electromagnetic power produced, which is gross power, C. The internal electromagnetic torque, D. Applied torque if rotational loss is 10 kilowatts, E. Efficiency of the generator, and voltage regulation. This is the handwriting of the same problem seen from the whiteboard of the classroom, so there is nothing different than the previous slide. Let's remember some rated values given in the problem. 240 kilowatts is the rated power of the electrical machine. 240 volts is the rated output voltage at the load. Load is taken as the reference, and the machine is being operated as DC generator, and 600 RPM is assumed to be the rated speed, and this 600 RPM is revolutions per minute, and it can be converted to radians per second as 20 pi radians per second. This is the angular speed, rated angular speed of this machine. And in the question it's given as this machine is used as separately excited DC generator. Its diagram is as shown. The separately excitation side is here, and the field is separately excited, and armature is, of course, there's a mechanical prime mover here, is rotating the armature. So the load is connected at the armature terminals. So the first thing is, let's convert these numbers to the magnetization characteristics. These numbers are given at 600 RPM, and the magnetization characteristic of the machine is drawn on the following page. So this is the magnetization curve, and horizontal axis is the field current. So this is horizontal axis, the first row, and vertical axis is the induced voltage, and the units are amperes and volts respectively. And we have 8 different value pairs, and these are shown with thick dots in the magnetization. So we have almost linear and then saturation region. Actually we started from 0, but it's the idealist case. Usually these type of machines, the machine will start some positive DC voltage. It's not given in the problem core. So practically it actually follows that red portion and then saturates. In this problem, if the DC generator is delivering rated voltage and it's driven at 600 RPMs, we will determine some 6 sub-items starting from induced armature EMF up to voltage regulation as given in the first slide. So part A, let's calculate the induced armature EMF. So this side is the field or separate excitation. Field voltage, DC voltage is given as 100 volts. We have some extra resistor to adjust current, and field resistance is 30 ohms. And we do have armature. Of course, the shaft is rotated by a prime mover, which is not shown here. And armature resistance, and through the resistance, armature current flows, and the load also receives rated power at the rated voltage output. So we start from the known quantities. Terminal voltage is 240 volts. Rated current is 1000 amperes. How did we find this? We found from the formula of power. We know the rated value, so rated current is or can be calculated as 1000 amperes. So there's a voltage drop across this resistor. So induced armature voltage equals to terminal voltage plus that voltage drop. If we calculate, we end up with induced armature voltage is 250 volts. So this voltage is induced at the armature. Part A is complete. Part B, internal electromagnetic power produced by this machine. So for the armature side, we have calculated the armature voltage. It's under the field excitation, and the torque is proportional with the field flux and associated rotor flux with some constant, multiplied with a constant depending on the number of windings, geometrical structure, size, length, etc., etc. And this torque creates power under rotation. Electromagnetic torque is produced by EA, or induced voltage, times armature current in terms of electrical quantities. So mechanical power input to this system creates electrical power output from this system. So the electrical power output from the armature is, we know the voltage EA and current, it ends up to be 250 kilowatts. So we continue. The applied torque, if the rotation loss is 10 kilowatts, is given in the question. So we do have prime mover, and DC generator in the problem produces rated 240 kilowatts at 240 volts at the load. And we know that the mechanical losses in the friction, etc., here, okay, is 10 kilowatts. The gross electrical power, EA times IA, was 250 kilowatts, calculated in the previous section. So net mechanical input E can be calculated as an additional output plus losses kind of equation, which ends up to be 260 kilowatts. So we can calculate the efficiency of the generator because we have net outputs and losses, etc. So total power input to the system from the mechanical side is the sum of all powers and losses, etc. So this 240 kilowatts is the output at the load. So V terminal times I terminal, or this also equals to I sub A. So it's the rated power output at the load. We do have 10 kilowatts in the mechanical losses. We do have 10 kilowatts calculated from IA square RA. IA was 1000. So if we multiply these quantities, we end up with 10 kilowatts. and this term, which is the power loss at the field winding. So field voltage over the total resistance in the field. That ends up 260.25 kilowatts. Sometimes you may neglect this, but in my opinion we have to also include this because that power is lost in the field by some heating loss, etc. So the efficiency is 240 kilowatts over 260.25, roughly 92%. In the last section, voltage regulation can be calculated by the difference in no load to full load voltage divided by full load. So full load is 240 volts. The no load voltage is found by removing the rated load in this problem by keeping other parameters, speed, field current, etc. Constant. So we just remove the load and measure the output voltage. So this is our system. All the system is shown. Field excitation here. So total field resistance is 40 ohms. Field current is 2.5 amperes. Armature voltage is 250 volts. Voltage drop is 10 volts, and load resistance. Load current is at rated. Load voltage is again at rated, and load is at rated power. So if we remove this resistance out, the open circuit voltage equals to 250 volts. So the regulation can be calculated by taking the difference and dividing by full load voltage and expressing in percentage, gives us 4.16%. So if we summarize, in the magnetization curve, this is the point of induced voltage, and from this curve we graphically determine the field current about 2.5 amperes. That's the reason in the field circuit our external is 10 ohms and field resistance is 30 ohms, so total is 40 ohms. So this is our operating point for this problem. For example, assume the machine in the previous problem is running in Turkey, and its operating characteristics have been calculated as shown in the previous slides. New question that was asked in one of my lectures. This machine is transferred to a country where the mains frequency is 60 Hz. What parameters will change in the problem? So that was a good question. So you may think of changing the frequency of operation of the main supply for this machine. Will it operate with the same parameters as the parameters given in the problem or not? The answer is nothing changed. In our third year grade ELE 361 electrical machinery course. Because this is a DC machine and we have ignored alternating current effects in our machines. Inductance, etc. are all cancelled out. But in real life, depending on induced voltages and currents onto electrical system, the method of rectification from AC mains. Okay, this is related to, for example, obtaining the field voltage, and that also will affect the field flux. This will change magnetization characteristics, and then the operating point, some electrical losses, etc. will slightly change, and your machine will operate on a slightly different operating point in another country. But we cannot determine how much deviation will occur. Also, the temperature and other climate effects will play a role as well. So that ends our problem related to the example given in the lecture slides.